Testing. Okay, good morning, student. This is Henry Lok. Welcome to join our lectures again, free view of lecture 2. Before starting our class, I want to remind you that we have one assignment which is going to submit very soon. The due date of this assignment 1 is 14 October. I think it's next week. Yes, next week, Friday. Make sure that you submit on time. You can upload your solution on Moodle. There are 3 questions. The first one is about trust analysis using Sybas method. The second one is beam analysis using Sybas method. And the last one, frame. Now you should be able to finish all 3 questions. We have similar example in our notes or tutorial, right? Any questions you want to ask me regarding to this assignment? No 問題? Finished easy. Yeah, that's the good news. Make sure that you submit on time. You can upload your answer to Moodle. I think I have already opened the assignment box on Moodle. You can upload your answer right here. Submission, assignment 1. So, as usual, normally I start from the Q&A sections to see if there's any questions you want to ask me regarding to the lecture materials or the other thing else. Last week is week 5. We has already finished our lab. We finished our first workshop, and then last week we finished all the things regarding to Sybas method. And then we start a little bit to introduce what is structural dynamics. Last time. This is where we are at this moment. This week is week 6. I think no questions, right? If there's no questions, maybe we can continue our discussions on about structural dynamics. As usual, I will have a short revision before starting our materials. Okay, this is topic 4. Topic 4, the first part of structural dynamics. In topic 4, we are going to introduce what is structural dynamic system. We would like to know how to formulate the problems, how that means derive the so-called equation of motions. And then we would like to consider some additional effects like the gravitational force and support movement. I think last time we stopped around here, section 2. But I would like to go through the materials again because this one is a new chapter. I think it's good to have some recap. So firstly, when you want to solve a dynamic problems, in the past, for static problem, you simply use equilibrium, or you may use the simplest method, Q equal to K times D, etc. But when we go into another topic, structural dynamics, we need to consider another equation, which is a more general form. We so-called, you can derive this using Newton's second law. And there are some notation you have to familiar with. U mean displacement, U double dot mean acceleration. You have to familiar with this kind of symbol. And then we introduced some characteristic last time. For our dynamic problems, everything becomes time varying in nature. The force, the displacement, the velocity, acceleration, everything changes with time, not a single values. This is one major difference between static and dynamics. And then we have to consider inertial force. The mass start to contribute into our equations. You will see where are they in our equation very soon. And then the last one, and also one new concept, energy dissipation. Energy dissipation means energy loss. For a dynamic system, we need to consider energy. We have to consider the energy loss mechanisms. So in the formula, you also observe there is one term related to energy dissipation. We call it damping. Because of energy dissipation, the oscillation amplitude will start to decrease with time goes on. You will learn how to derive this. What I mean is that you will learn how to draw this graph in these lectures, and because I believe that in this lecture, we can move to topic 5, free vibrations. Actually, I just copied from topic 5. And then the second part is about structural idealizations, how to simplify the problem to formulate our equations. At the beginning, we start from single degree of freedom system. Single degree of freedom system means we only consider one single degree of freedom, normally the horizontal displacement, one displacement. And then for this single degree of freedom system, all the structural property can be described using 3 parameters: M, mass, K, the total lateral stiffness provided by columns, and finally C, damping coefficients, which is used to describe the energy loss mechanisms, the total energy loss. So we use 3 simple parameters: total mass, total stiffness, total damping, to describe one simple dynamic system, SDF. We have short discussions last time about what is elastic force. From this elastic restoring force equation, you can see what is stiffness. Stiffness simply means the relationship between force and displacement. And this is the stiffness in the past, we call this stiffness constant in your physics module. Similar concept. But for our structures, for our whole structures, you can calculate stiffness yourself based on the property of the members, beam or columns. Normally, we make 2 assumptions: rigid beam or flexible beam, rigid slab or flexible slab, 2 extreme scenarios. The first one assumes that the slab or the beam is totally rigid. In this case, the total stiffness of a system is equal to the stiffness of column times the number of columns. The more the column, the higher the stiffness. Each column, the stiffness is equal to 12 EIC over H cube. And then another extreme scenario is flexible. The slab is totally flexible, no rigidity. In this case, the column stiffness becomes lesser, 3 EIC over H cube, and then multiply by the number of columns to see how many columns you have. These are 2 boundaries, maximum, minimum. We normally use this kind of value to do our formulations. Otherwise, there's no easy way to find out the stiffness K. Stiffness is easy because it's just like what you learned before in static. It is a restoring force provided by column, provided by beam, this kind of materials. And other new things is damping. Damping is quite complicated because in reality, you have many different energy dissipation mechanisms in a building. Maybe due to temperature, heat loss, friction, or cracking. There are many mechanisms. There is no easy way to formulate all mechanisms individually. That's why in last time we introduced that we normally use one very simple model, viscous damping model. According to this model, all the energy loss, all the energy dissipation mechanism can be described by one simple terms, damping coefficient C. We call that viscous damping coefficients. In short, damping coefficients. It is used to model all the energy dissipations, make things simple. Last time I think I'm stopped here, equation of motion. This is the Galvin equation for single degree of freedom system. Maybe today we start from here again. Newton's law. Newton's law, you can use Newton's law to derive our equation of motion for our dynamic systems. Newton's law tells us one thing: net force equal to mass times accelerations. Net force is equal to external force minus internal force. What is external force? External force, according to this single degree of freedom system model, on the top right-hand corner, we have a single degree of freedom system model. This system characterized by 3 parameters, M, C, K, and it is under one dynamic force, P. P is an arbitrary dynamic force. It can be a sine function, cosine function, arbitrary function, any loadings. It can be static as well. Static is just one special case of dynamics. Go back to this Newton's second law. Net force equal to external force minus internal force. External force means to apply loading, P. Internal force. According to this system, we have 2 resistance to resist the motion. The first one is due to the stiffness. The other one is provided by the damping mechanisms. So there are two resistance to resist the motion, resist the applied loadings. Symbolically, I call this Sibelius force, Fs. For the energy loss, for the damping terms, I call this Fd symbolically. P minus Fs minus Fd equal to Ma. This is the Newton's second law again. This equation is general. It can be applied to any Sibelius model, any damping models in general. According to the previous sections, we can assume that stiffness is equal to K times the displacement. Damping force is equal to the damping coefficients times the velocity. So according to this linear model, you can replace Fd by Cu dot. Cu dot mean velocity. U dot mean velocity. Du dt. So you can replace our original formula to this simple form. Applied loading is equal to mass times the acceleration plus the damping coefficients times the velocity plus the stiffness times displacement. If you want to understand the behavior of this single degree of freedom system, if you want to know how it oscillates, how it moves, how it accelerates, then your task is to solve for this equation under the applied loading. Depends on the function of the loading, you can solve it mathematically. Find out the expressions of U equal to something. It becomes a mathematical problems. We're actually in our module here, topic 4 focus on formulations. That means these equations. And then in the following topics, topic 5, topic 6, and topic 7, we will start to solve this equation under different loadings. Okay, in the following topics, topic 4, 5, topic 5, 6, 7, we are going to solve this equation under different applied loading. Today, we will start to handle the most easiest scenario, free vibrations. This one is linear system. Linear system. Because we assume that displacement linear proportional to stiffness, the velocity linear proportional to the damping force is linear proportional to the velocity through a constant, linear. It can be nonlinear in reality, but in this module, we just consider linear to make things simple. Nonlinear means they are not a straight line, right? In the previous model, we assumed that they are straight line. Damping force linear proportional to velocity, stiffness proportional to displacement. But in reality, it can be nonlinear. But anyway, in this model, in these lectures, in this module, we just consider linear system to make things simple. If you want to know more, you may read the textbook. The textbook also consider a little bit about nonlinear system. So from these equations, you can see that initial force start to introduce in our equations, right? Mu double dot. You can see that our mass now play some role in our formula. Right? In the past for static, you cannot see the contribution of mass easily. But here, dynamics, mass and acceleration gives you something. The middle terms, the second term is related to damping energy loss, damping components. And the last one is stiffness term. One interesting thing you can observe from this formula. In the past, static. Static means the system has no acceleration, low velocity, right? For static problem, the structure will display, but the structure will not move, they will not accelerate, right? For a static problem. So when you substitute velocity and acceleration equal to 0, back to this formula. This one disappear, this one disappear. It becomes what? It becomes your classical formula. Force equal to stiffness times displacement. Right? Actually, you can convert this equation of motion, back to static model by substituting velocity, acceleration equal to 0. So it's proved that static is just one special scenario of dynamics in which velocity, acceleration equal to 0. But anyway, in these sections, we need to consider dynamic. So the system has velocity and accelerations. Otherwise, we have nothing to discuss. When you read the textbook, there is another principle to derive the equation of motion. You can derive equation of motion using Newton's second law. That is not normally what I use. But in the other way, there is another approach called the Lambert's principle. You can derive the equation of motion, this one, using the Lambert principle. And what about this principle? This principle is based on a concept called dynamic equilibrium. Dynamic equilibrium. According to this guy, he introduced one extra force called fictitious inertial force. Fictitious means something like virtual inertial force. It's just like one resistance, just like the stiffness, just like the damping. The mass, the inertial effect, provide one extra resistance, which is mass times acceleration. So graphically, there are three resistant forces against the external force. They are the stiffness force, they are the damping force, and the last one is the inertial force. From this picture, you can consider just like equilibrium. Right? What is equilibrium? Summation force equal to 0. But this time you need to consider this fictitious inertial force as well in your formulations. So when you consider dynamic equilibrium equal to 0, external force equal to Fi plus Fd plus Fs. So it also gives you the same outcome. So you can derive this equation using Newton's second law, just like what we did before on the previous page here. You can use Newton's second law to derive equation of motion. Or if you like, you may use so-called dynamic equilibrium. They give you the same outcome. Normally, I use Newton's second law. But sometimes the Lambert's principle may be slightly more easy to understand because it's utilized something like equilibrium. But you have to introduce this inertial force. Otherwise, there will be some problems. Okay, then how to use the equations? Well, one simple example. In this example 1, you are asked to derive the equation of motion for the following one-story RC frame. Take a look on this problem. We have a beam on the top. The beam is totally rigid. The stiffness of the beam is equal to infinity. If you remember what we mentioned before, we have two extreme scenarios when you want to calculate stiffness: flexible slab or rigid slab. Actually, this symbol tells you the conditions. This belongs to the rigid slab situations. The mass on the top is equal to m. We have a mass here. The mass equal to m. The mass of column is massless. You can ignore the mass of column. This is normally what we assume for single degree of freedom system. The column stiffness, EIC for each column. The height of the column is h. Assume that these single-story structures under one dynamic force, a sinusoidal force, a psi force. If you plot the function of this loading, P versus T, you can see that it is a psi force. And the magnitude is equal to P, capital P. It's not a constant, but it's a time varying function. Maximum, minimum, alternatively, a sinusoidal force. But in these questions, we just asked you to formulate the equation of motion, not solving the response. You will know how to solve this response not very soon. Maybe I think in next class, topic 6. Topic 6, we try to handle this sinusoidal force. But in topic 4, we just focus on formulations. What about the formula? The equation of motion for this system. If you like, you may use the equation. If you like, you may derive from the first principle. You may derive the equation from Newton's second law, or you may derive the equation using the Lambert's principle. Up to you. But you can directly apply this formula because in the notes I give you the formula already. Why don't we use it? Right? You can use this formula directly. For single degree of freedom system, the equation should be looked in this manner. Right? For a single degree of freedom system, everything characterized by only 3 parameters, M, C, K. So right here, you just need to find out what is M, C, K for this problem. We know the formula, right? P, T equal to mu double dot plus dot 1, dot 2 plus cu dot plus ku. This is the equation of motion for a single degree of freedom system. Actually, you know the answer. You just need to evaluate the three parameters, M, C, K. What is M, what is C, what is K? So it's actually not a very difficult problem. You just based on the given information, find out what is MCK. M is easy because the picture gives you the answer. M is just M, mass, total mass of the system. Because we ignore the mass of column. So mass is mass, M. You have to calculate C and K yourself. C is also given at the middle. C is used to describe the total stiffness of a system. C is used to describe the total damping property of a system. Normally, it's represented by something like a dashboard, C. So C is also well defined in this problem. So in this problem, actually asking you to determine stiffness, K. What is K? K means the total lateral stiffness. When the system displays horizontally, the column try to restrain the motions, right? Give you some stiffness. So this problem asks you to evaluate what is K. According to our discussion before, we have two extreme scenarios, flexible slab or rigid slab. In this problem, example 1, it belongs to rigid, right? The beam is totally, the factor rigidity of beam is infinity, which means rigid. For rigid beam assumptions, the column stiffness for each column is equal to tau EIC over H cube. We have two columns in this problem, column 1, column 2. So you just need to multiply this K column by 2. It becomes the total stiffness of the whole system, 24 EI over H cube. Okay, you can use this kind of outcome directly. You don't need to prove it to me. You can use this outcome if you found that it is rigid slab. You may use the other equation if it is flexible slab. So read the question carefully. This kind of property will be given, flexible beam or rigid beam. So read the question carefully. And you can also recall what you have learned in your physics module. In your physics module, you have learned how to combine the string stiffness together. You have system in parallel. And then you have another scenario, spring in series. Right? In your physics module, you have learned how to combine stiffness, K1, K2 together to obtain the so-called equivalent stiffness. This frame structure is just like a parallel system in fact. What is the criteria for parallel system? Parallel system means all springs under the same displacement. When this system displays horizontally, spring 1, spring 2 under the same displacement. Go back to this problem. When this structure displays horizontally, column 1 and column 2 under the same displacement. So mathematically, they are equivalent. That's why I put down a remark here. It is in parallel. For a parallel system, how to find the total stiffness? K1 plus K2 simply means times 2 because they are identical. Okay? Then you can think about what happens if they are in series. In series, how to calculate the equivalent stiffness. Okay? You can think about this problem. I believe that you will see in parallel very soon, in series very soon. But anyway, we have the K. We have K. Substitute K back to the formula. Then it becomes what you need in this problem. This is the equation of motion for this one-story frame structures under sinusoidal force. If you know how to solve it, then it is a good news. That means you are expert in single degree freedom system. You know how to determine their response. Have you done that before? How to solve these equations? I believe that maybe you are learning or you have learned already, right? In your advanced mathematics. You have already learned how to solve second order non-homogeneous differential equations. If you forget, it doesn't matter because I will recap a little bit about the important concepts. This is example one. Example one just asks you to formulate the problem, not solving it. Just asks you to formulate the problems, formulate the equations. We will discuss how to solve it for our Sandler force. We will discuss in topic 6. Topic 6. Okay, equation of motion. Then what next? Section 3 and section 4. We are going to consider two additional effects. The first one is gravitational force effect. The other one is due to the support movement or support excitations. Support excitations means support movement. Normally, it used to represent earthquake attack. But let us start to introduce the gravitational effect first. In the previous example, we consider a system under horizontal movement, horizontal force. For a system under horizontal force, you don't need to consider the gravitational acceleration. What is the impact of gravitational acceleration? The gravitational field gives you set weight. The gravitational field gives you set weight. Set weight is something like external force. But in the previous formula, we did not consider set weight, because in the previous sections, we consider horizontal movement, in which the direction is orthogonal to the set weight. Orthogonal, then you don't need to consider perpendicular to each other. That's why in the previous formula, we don't need to consider set weight effect, because they're perpendicular to each other. But what happens if we consider vertical vibrations? If we consider a system under vertical vibrations, then this time you have to start to consider the effect of gravitational field. So in section 3 here, in section 3, we try to change our direction a little bit. We try to consider vertical vibrations, not horizontal. I just want a simple example to show you the effect, the influence, what happens if for a system under vertical vibrations. Have a look at this example. We have a beam, cantilever beam. This end is fixed. The other is free. On the right-hand side of this beam, it's attached to a mass, a concentrated mass through a spring. And then from the picture, you can see that spring has a spring constant. The beam length is L. The beam should have its fractional rigidity. Maybe I call this EIB. Beam has stiffness, correct? EIB. And the mass has set weight mg. This mass has set weight. On top of that, we have external force T along the vertical directions. So from this picture, you can observe that the system is start to vibrate vertically, not horizontally. So answer the same questions. Try to formulate the equation of motion for the mass, for this concentrated mass M under this vertical force under for this system. Cantilever beam. To make the equation, to make the problem slightly more easier, we assume that C is equal to 0. We ignore damping effect in this example. Just consider stiffness, just consider mass to make the equation slightly easier to formulate. Equation of motion. This time is under vertical vibrations, not horizontal. So you have to consider set weight, mg. This time we have no choice. We have to start from our first principle. You can derive the equation using the Lambert's principle or using Newton's second law. Before showing you the Newton's second law, I use one picture to show you the deformation of a system. And then I will also introduce some parameter to describe displacement. The first one is here. assume that before any deformations, the beam remain horizontally. Right? Before any deformation occurred, the beam remain horizontal. The spring undeformed. So this level is our undeformed positions at the beginning. Everything at rest, no movement. We take this as reference. This is our reference 0, everything undeformed. The beam, no diffraction. The spring, no elongation. You can measure your displacement from this undeformed position to their current level. So for example, at time equal to t1, just arbitrary time instant, the displacement measured from the undeformed level is described using a symbol u bar. You can describe displacement from their undeformed positions. I use a symbol u bar for this measurement, measured from the undeformed positions. Then what about the other two parameters, delta and u? Well, I would like to introduce another reference level called static. If you ignore dynamic force, if you ignore dynamics, then you can find out the static positions of this set weight and of this mass under their set weight. How to understand this the statement, static displacement due to own set weight? Normally, I'll use one example. If you allow this system to vibrate vertically, at the beginning, it may have large displacement at the beginning. But in case if you consider energy loss, what will happen? The displacement amplitude will start to decrease, right, because of energy loss. And finally, it will rest at one level as time goes on. Right? As time tends to become a large number, as time goes on, if there is damping, the system, the mass, will finally stay at rest at one level. That level is called static displacement. Because as time goes on, the system remains at rest. At rest means they are static. The displacement at that time becomes your so-called static displacement. How to find out this level? If you know the stiffness, if you know the set weight, I use a symbol delta ST. According to static, set weight W equal to stiffness times the displacement, static displacement. Static. Set weight W equal to the stiffness of the system. Maybe I put the symbol in more precise manner. The system stiffness times the displacement, static displacement. You can change this formula a little bit to find out so-called delta ST. It represents what happens as time goes on. Static. If you like, you can measure displacement from this static equilibrium level. And then I use the other symbol U to denote the displacement. U is a displacement measured from static equilibrium, while U bar is a displacement measured from the undeformed positions. Okay, these are the meaning for these three parameters, U bar, delta ST, and U. You may wonder why we need to consider two different displacement measurements in this formula, in this problem. And actually, this one is a very smart approach to formulate the problem. You will see why it's a very smart approach on the next page. At the beginning, let us use the undeformed position, undeformed level here to measure our displacement. We use U bar at the beginning. We use U bar to formulate our problems. Suppose we have a mass, not suppose. In this problem, we have a mass at the tip, at the free end of the cantilever beam. This mass has a set weight, and then we have applied loading, dynamic force P, according to our problems. Normally, there are two resistance. Normally, there are two resistance against the applied loading, right? The damping force and the stiffness force. Stiffness force equal to the system stiffness time the displacement. We use the undeformed positions at the beginning. So the static force is equal to system stiffness times U bar. Normally there is a damping force, but in this problem, to make things simple, we assume that no damping. try to make the formulation more easy at the beginning. So what we have, you can use Newton's second law, external force minus internal force equal to ma. Newton's second law, external force minus internal force equal to ma. This is the formula, Newton's second law. External force on the left-hand side, internal force. I move the internal force to the right-hand side of the equation, and then this is ma. U double dot mean acceleration, but we use the symbol u bar rather than u in this formula. We use undefined positions as our reference level at the beginning. So this is the equation of motion for this system. P is the dynamic loading, W is the set weight, KE is the effective stiffness of the whole system. I will talk about is the effective stiffness. Because in this problem, spring, when this mass is displayed vertically, spring under elongation, beam under deflections. The beam also provides some stiffness for the system. Just like column. Column has the, you can convert column to stiffness, right? For beam, you can also express the stiffness using the beam property. So when you combine the stiffness for whatever the beam and the spring together, then it becomes so-called effective stiffness. I will mention how to calculate effective stiffness later. Let me think about yourself at this moment. Can we use the parallel system right here? Okay, continue our formulations, not yet finished. Here we use U bar to define all the parameters, but we can simplify the problem a little bit. U bar, according to the previous page, U bar equal to U plus delta ST. From this picture, U bar equal to U plus delta ST. Just add up these two numbers together. It becomes U bar. We can simplify this equation a little bit. Let me have a look at the remarks on the right-hand side of this page. U bar equal to U plus delta ST. If we differentiate this equation with respect to time, U bar dot equal to U dot plus delta ST dot. You can use change rule, right? When if you differentiate one equations, then you can use, I think this one is additional rule. It's become U dot plus U delta ST dot. What is delta ST dot? Differentiate delta ST with respect to time. Symbolically, which means you also evaluate delta ST dt. Then you need to ask yourself, what is delta ST? Delta ST is static displacement, static. How to calculate delta ST? From static, set weight equal to the system stiffness times the static displacement. From this equation, you can see that delta ST depends on the set weight, mg, depends on the stiffness of the system, ke. So if we differentiate this equation with respect to time, what will happen? Set weight, independence to the time. Stiffness also independence to the time, right? So if we differentiate this equation with respect to time, it will give you 0. 0. So if we differentiate this equation, U bar, then it will give one equation, U bar dot equal to U dot, and then plus 0. Differentiate this equation once more time. With respect to time, it becomes U bar double dot plus U double equal to U double dot. Okay, this is how you can get this formula. Just simply differentiate this equation twice with respect to time. Okay, delta ST is independent to the time, so when you differentiate, it becomes 0. The second equation, to understand this equation, you may consider just like a static problem. I think I put a picture at the bottom. Yeah. It's just like a ball sitting on a platform. When this ball has a set weight, right? When this ball sitting on a platform, it will settle downward. If there is a spring supporting the platform, you can use the spring constant, use the set weight to evaluate the settlement, delta st. So it's just like a static equation for this equation 2. You can understand using these easy mechanisms. So we put this kind of property back to the formula. U bar double dot equal to U double dot, right, because of this equation. And then W on the left-hand side is equal to KE times delta ST. So you can cancel out W and KE delta ST on the right-hand side of these equations. Then what remains? After this cancellation, the left-hand side has only P. The right-hand side, U mu double dot plus KE U. This equation, in terms of the formula, this equation just like what we learned in example 1, a system under horizontal movement. And then the set weight disappeared from the equations. This is the first smart approach to measure displacement from our static equilibrium rather than the undeformed positions. Because when you measure displacement from the static equilibrium positions, then the formula, you cannot see the effect of set weight. In the other words, for a system under vertical vibrations, if you measure displacement from the static equilibrium level here, then mathematically, it is equivalent to a system under horizontal vibrations. You can use the equation of motion directly without considering the set weight. This is what we can conclude from this example 2. You can measure from undeformed positions, but it will make the equation slightly more complicated, because if you measure from the undeformed position, there is one extra constant on the right-hand side. In case if you measure from the static equilibrium positions, then it's just like a horizontal vibrations. No need to consider set weight. Okay, this is what we can observe from this example 2. So when a system under vertical vibrations, we still able to formulate the equations of motion in this way. The last problem for this example 2 is, what is KE? I mentioned that KE is the total stiffness by considering the beam, diffractions, and the spring elongations. How to calculate effective stiffness? We have a beam, we have a spring. We have beam, we have spring for this system. Beam under diffraction, spring under elongation. How to combine their stiffness together? Can we just add them up, just like what we did in example 1? You need to think about so-called the parallel system and series system. I just mentioned the parallel system criteria. Parallel system means all spring under the same deformations. But what about our current problem? Are they under the same deformations? Well, the answer is no, they are not under the same deformations. The beam diffract vertically, the spring under elongation, and then the mass at the bottom. The deformation of the beam and the deformation of the spring, they're obviously different. They are not under the same deformations. So in terms of physics, you cannot use the parallel model because they are under different deformations. Different from what we learned in example 1. Example 1, we consider 2 columns under vertical movement, and in which they are under the same diffractions. So not the same case. Actually, this one is belong to series system, not parallel. Series system in this one, a spring, 1 spring, 2 spring, they're under 1 force. Spring 1, spring 2. You can see that for a series system, each spring under the same force. Spring 1 under F, spring 2 under also F. For a series system, they're under the same force. Just like this example. A mass here under a force Fs, this force transmitted to the beam through a spring with the same value in series. For series, how to calculate the stiffness? According to our physics, 1 over the equivalent stiffness of the system equal to 1 over K1 plus 1 over K2. If you have more spring, then you can put more terms on the right-hand side. So here, for a series system, 1 over stiffness, Ke is the equivalent stiffness of the whole system, equal to 1 over K beam plus 1 over K spring. K spring is given. I think it's K, right? We call this K in the problems. Then what is K beam? When this beam diffracts, you have to find out the corresponding stiffness. This one is a cantilever beam. For a cantilever beam under this diffraction due to a point load, you may treat this as a static problem, find out the force displacement relationship. You have a lot of practice to determine how to find out diffraction of a system. For cantilever beam, you can also find out the diffractions under applied loading P. The factor here is the stiffness, which is equal to 3EI over L crit. If you're familiar with statics, then you can get this diffraction easily. So here I just give you the outcome. K beam, for a beam under force at the tip. The corresponding stiffness is equal to 3EI over L crit. K beam. K spring is just the stiffness of the spring constant, simply speaking, K. So you can put them together if it comes to equivalent stiffness. Our equation of motion measured from the static equilibrium positions. Okay, for mathematics, right? This is structural dynamics. You have to recall what you have learned before in your physics module, in your structural analysis module, combine the concept together. Whenever you will see this kind of formula many times in this module. Sometimes they're in parallel, sometimes they're in series. Normally these two, right? Series, parallel. So in this notes, I showed you these two scenarios. For a system under horizontal movement, just like example 1, you may use parallel system, add up the column stiffness together. For a system under vertical vibration attached to a spring, something like that, then it belongs to series. For series, you can use the formula like right here to find out the equivalent stiffness. Parallel series. This chapter also focuses on formulation, not solving the problem. We will learn how to solve this equation in the next chapter. This kind of equations in the next chapter, topic 5 and topic 6. The last part, section 4, we would like to consider the effects of ground the support movement, support excitations. Support excitations means support movement. Normally used to model a system under earthquake. Ground excitations. Structural dynamics is normally applied to a system under earthquake. For earthquake, you have to treat this as a dynamic loading, just like the picture at the bottom. Assuming that we have a single degree of freedom system, lump mass, we have total stiffness, total damping ratio, damping coefficients, and the ground excitations. For an earthquake, we normally represent earthquake using the ground accelerations. UG, the subscript G mean ground, double dot mean acceleration. So U double dot G represent the ground accelerations. You can use some machine to record the ground acceleration due to one earthquake. If you want to measure determine the response of structures under a particular earthquake, then you need to know the earthquake history. The earthquake history described by U double dot G. At different time instant, you have different numbers. You can measure by putting a machine, equipment, device on the ground or the other platform to measure what happened under an earthquake. So what about the equation of motion if a system under ground acceleration? There is no applied loading. You cannot see any force. There's no force acting on the system, right? You cannot see a P applied on the system, right? No force. Then how to formulate the equation of motion for this system? Ground accelerations. We have M, we have C, we have K, but no force. This one, in some sense, this one is similar, quite similar to example 2. You have to introduce different deformation parameters. At the beginning, this is the initial positions of this building. Now the ground start to oscillate, start to move. So you can see that the ground movement, the ground with the structure displayed horizontally. Ground displacement. I use the symbol UG to denote the ground displacement. The ground is not fixed. The ground is movable right now because of earthquake. The ground movement is denoted by UG. The system itself, the column, the beam can also under movement. The beam or the column movement is described using another symbol, relative displacement. I use U on this line. U is the relative displacement due to the effect of the column deformations. Okay, so you can see that for our structures under ground movement, you also need to introduce different parameters to describe their deformations. So that's why it's a little bit quite similar to example 2. You cannot just use one U. There are two U in this problem, UG and U, the relative displacement. And what about the total? The total displacement means UG plus U, UG plus U. Some textbooks call this absolute acceleration. Some textbooks call this absolute acceleration. But I think using total is more easy to understand from our point of view. Total just like add up the things together. But when you read some textbook, they call this absolute displacement. So you may put a remark yourself here. Absolute means similar things. So how about our equation of motion? For a single degree of freedom system under horizontal movement, we consider horizontal movement again. Our equation of motion becomes this form. For single degree of freedom system, they normally look in this manner, right? mu double dot plus cu dot plus ku. For single degree of freedom system, you can normally express the equation of motion in this way. And then you just find out what is m, what is c, what is k, just like what we did in example 1. In this simple problem, we have m, c, k divided. But you can see one interesting thing. On the right-hand side, 0. Because the system has no applied loading, P equal to 0. So when you set up the equation of motion, P, 0. mu double dot t plus cu dot plus ku equal to 0. What is ut? Ut means the total deformation. We just showed you on the previous page. The inertial force depends on the acceleration of the total displacement, double dot. While the resistance provided by damping, provided by the stiffness, depends on the relative deformation of the column here. The stiffness provided by column depends on U, not UT. Right? The stiffness term depends on U, not UT. Depends on the elongation of the spring, right? Or the movement of the columns. Nothing to do with the ground accelerations. The ground movements. So you can see that for the acceleration term, we use UT. For the stiffness and damping terms, we just use U rather than UT. UT equal to summation of U double dot and UG double dot plus cu dot plus ku. You can move U and U double dot G to the right hand side of these equations, and then keep everything related to U on the left hand side. u double dot plus cu dot plus ku equal to minus mu double dot g. This is the force induced by earthquake. To make things more clear, you can replace minus mu double dot g using p again. Then you can find the formula. It's just like what you learned in example 1. mu double dot plus cu dot plus ku equal to p. It's just like a system under loading, in which the loading is induced by earthquake. So you can see that we normally can change the problem back to this something like a classical form, right? mu double dot plus cu dot plus ku equal to force. The force can be due to applied loading, can be due to earthquake, or can be due to step weight or the other thing else. The force induced by earthquake mathematically is equal to minus mass times the ground acceleration history. So if you want to find out the response of a single degree of freedom system under earthquake, then it's equivalent to asking you to solve this problem, solve this equation, find out what is u, t. But you know the answer is not easy because earthquake acceleration is not regular function. Normally, earthquake acceleration is something like a random variations, arbitrary. It's not a psi function, it's not a cosine function. So it's quite difficult to find out the result, u, of this single degree of freedom system. In topic 7, I will let you know how to play with a system under arbitrary loading using so-called numerical method. So under all kinds of loadings, we have some way to find out the response. But a short summary, in this chapter, you have learned several things. Firstly, we know the difference between static and dynamics. There are 3 main differences, right? For a dynamic problem, everything is time varying nature. And then you need to consider inertial force, MA, right? And then you need to consider damping, energy loss, dynamics. And then we introduce dynamic property. For a single degree of freedom system, we have M, we have C, we have K. They're used to describe the system properties, MCK. And then finally, we formulate the equation of motion for a single degree of freedom system under different conditions. Horizontal vibration, vertical vibrations, and finally, we consider ground excitations. These are all things we mentioned in this chapter. Formulations. The next one, topic 5. Topic 5, we will try to consider how to solve the problem, how to solve the equation, not just formulate. We would like to solve the problem and find out the displacement function, how the system oscillates under different kinds of loadings. End of chapter 4. Okay, let's have a short break. After the break, we will enter another new topic, topic 5. Topic 5 is something related to free vibrations. Maybe we can take a short break for 5 minutes. Testing. So, well, this is the end of the first break. Before the break, we successfully finished topic 4, Introduction to Structural Dynamics. In topic 4, we basically handle formulation problem, how to formulate equation of motion for a single degree of freedom system under different loadings, under different conditions. Is there anything you want me to clarify? Easy, right? Topic 4, formulation. Right? We have not yet solved the problem. So actually, I think there's not a lot of things we can discuss at this moment. Topic 4 just focus on formulation. But in topic 5, topic 6, and topic 7, we need to solve the problem. Right. Topic 4 about basic formulation. But topic 5, topic 6, topic 7, where is topic 7? Oh, doesn't matter. Starting from topic 5, we will try to handle different scenarios, how to solve a system under loading, psi force, cosine force, arbitrary loading. We will discuss case by case. That's why I divided them into different topics. Topic 4, we will discuss the most simplest scenario, free vibrations. And then the next topic, topic 6, we discuss forced vibrations if there is applied loading on the structures of a single degree of freedom system. And then topic 7, I will upload today. Topic 7, we will handle a system under arbitrary loading, just like earthquake. After topic 7, we will go to multiple degree of freedom system. At that time, you will see your old friend again, matrix. Mass matrix, Sipers matrix, and damping matrix. This module have many matrix equations, unfortunately. So anyway, let's see if you have any questions. Another reminder, next week, you need to submit your assignment 1. Please spend some time to complete your assignment. There are only 3 questions. For some tasks, you may use computer software like Excel, MATLAB, Mathematica to help your calculations. Do not submit Excel directly on Moodle. You please convert them to PDF version, so that I can put some marks, put some writing on your answer script. Do not give me your Excel directly. Otherwise, I don't know how to mark your Excel. I will not look at your equation individually if you give me Excel, so please don't do it. And truss, beam, and frame. I think question 1, question 2, you can handle using hand calculation directly. For question 3, it involves a relatively large frame structures. For this one, I think using Excel will be very helpful. You can use Excel help you to add up the matrices together. You can use Excel to find out the inverse matrix, inverse K11, and then you can use Excel to do the matrix multiplication. Save you a lot of time. You can use copy and paste, copy the values from Excel to maybe Microsoft Word or the other word editing software. Yeah. 3 problems. So let us continue our discussions. Now we are going to enter another new topic, topic 5. Let me share the screen with you. Topic 5. Well, in the previous topic, topic 4, we discussed how to formulate our equation of motion for single degree of freedom system under horizontal, vertical vibrations. And what about here? In topic 5, we would like to consider one special scenario, a single degree of freedom system under a particular vibration mode. We call it free vibrations. We will start to solve the equation of motion from this simple scenario first, free vibrations. Firstly, we will introduce what is free vibrations, and then I will let you know how to solve the equation of motion for a dynamic problem under free vibrations. These are the content page of this particular chapter. At the beginning, we would like to solve the problem by considering undamped system, undamped free vibrations. We ignore damping, and then solve the problem, solve the equations. And then in section 2, we will consider more general situations in which we have damping. Then we will solve the problem again. Finally, I will talk a little bit about applications, how to apply the result from section 1, section 2 for some practical problems. At the beginning, let us discuss how to solve the equation of motion for undamped system under free vibrations. But firstly, what is free vibrations? What is the meaning of free vibrations? Maybe you have heard this term before in the other physics modules. Well, firstly, free vibrations mean there is no any applied loading. Free vibration means there's no applied loading, no dynamic force. P equal to 0. This is the definition of free vibrations, no force. You may ask, hey, if no force, then why the structure will oscillate back and forth? The reason is very simple, just like the example at the bottom. If you want to make the structure oscillate horizontally, what you can do? You can firstly display the object horizontally with a value u 0. This 0 means time equal to 0. At time equal to 0 means at the beginning. Okay? At time equal to 0, you display this object horizontally away from the equilibrium positions, the vertical positions. And then you release this structure, suddenly release this element. And what will happen? This mass will try to go back to the equilibrium positions, right? Because of the restoring force. But they will not stop at the middle suddenly. They will keep moving to the left-hand side, right? Because of inertia. They will keep moving to the left-hand side up to a certain level, at rest, and then go back to the right-hand side, and then go left, go right, go left, go right, back and forth. This is one way to excite the structure to undergo free vibrations. You give a structure some initial displacement or initial velocity, and then the structure will oscillate back and forth horizontally. This vibration mode, we call that free vibrations. There is no any applied loading. You just need to give the structure some initial conditions, initial displacement or initial velocity. Then the structure will oscillate back and forth. In this chapter 5, we would like to consider free vibrations with system no damping or with dampings. So the definition is easy, free vibrations. But what about a system, equation of motion under free vibrations? I just copied our equation of motion from topic 4. For a system, single degree of freedom system, the equation of motion normally look in this way. P equal to mu double dot plus u dot plus ku. If you put down this equation, then normally it's correct when you consider single degree of freedom system. Then you just like fill in the blanks, substitute your given information back to the equations. If there is no damping means C equal to 0. No damping without damping means there is no C, right? C is equal to 0. So the middle terms disappear, 0. If you consider free vibrations give you another conditions, P equal to 0. So you can also put this condition back to the formula, P equal to 0. Then you have the equation of motion for an undamped system under free vibrations. Like this. This is the equation of motion for one undamped single degree of freedom system under free vibrations. Mathematically, 0 equal to mu double dot plus ku. You are asked to solve for these second order homogeneous equations, and then you will know what happened for these structures. Your task is to solve this differential equation, find out u equal to something. This is what we have to do in this particular topic 5. If you want to know the free vibration response, then equivalent asking you to solve this homogeneous second order equation. Second order because second derivative. Homogeneous means the force, the terms equal to 0. Homogeneous. So it's relatively easy to solve for free vibration problems. Next time in topic 6. Topic 6, you need to consider forced vibrations. That means force is not 0. And then you need to solve a more complicated differential equations, non-homogeneous second order differential equations. To solve this problem, you need some initial conditions. You need two initial conditions, so-called the initial displacement. U0 means the initial displacement at time equal to 0. U dot 0 means the initial velocity. You need two initial conditions, U0, U dot 0. You can also understand easily, just like the example that I showed you before. You need to excite the structures, otherwise they will at rest forever, no movement. You need to give the structure some initial property, initial displacement or initial velocity. Otherwise, it does not move. It just stays vertically on the ground. So how to solve this problem? If you have already completed the advanced math module, then I believe that you know how to play with these equations. But for this module, theory of structure 2, this one is not a math module. It's an analysis module. So here I will solve the problem together with you, so you can directly use the outcome in the future. Okay? Normally, I will not ask you to derive the things. I just ask you to apply the formula. But to complete the story, please let me spend around 1 or 2 minutes and let you know how to solve the equations. We use one very, very simple technique to solve the equations. Solve for the unknown displacement. Differential equation 0 equal to mu double dot plus ku. I think the most easiest way to solve differential equation is to open your math textbook, because from your math textbook they have some general solution for different form of differential equations. Say for example, for homogeneous second order equations, the general solution normally expressed in this manner. The solution is equal to a coefficient cosine omega t plus another coefficient b sine omega t. This one is obtained from the math textbook. General solutions. What you have to do, you just need to find out the values a and b such that this equation can fit the differential equations. How to do it? You have you have displacement. Displacement is our general solution. Differentiate this general solution with respect to time. I believe that you have learned how to differentiate sine and cosine function. D cosine omega t, if you want. If you minus sine, you have to drag this omega out. D sine, D cosine, give you this pattern. Minus omega a sine omega t. D sine give you cosine, positive. Similarly, you have to move the omega outside the cosine function. So D sine give you omega b cosine omega nt. Testing you the knowledge of calculus, how to differentiate this kind of sine cosine functions. Why we use sine cosine? The answer is quite simple, because when you have a look of the original differential equations, it involves second order differentiation here. You can see that when you differentiate cosine twice, it will give you back cosine. Similarly, if you differentiate sine twice, it will give you back the sine function. So it seems that if you use sine cosine function as the general solution, you have some chance to fit this equation equal to 0, something like that. That's why using sine cosine is a valid solution form, because after second order differentiate, it will give you back the original pattern. Then what next? We can use our initial conditions. We have two initial conditions at time equal to 0. We have our initial displacement, we have our initial velocity, as given in the previous page. They are given. Right? You need to know the initial property, the initial movement, initial velocity. Otherwise, the system have no response. Use substitute t equal to 0 back to the upper two equations. For example, substitute u equal to 0, substitute t equal to 0 for our displacement functions. U0 equal to a cosine 0 plus b sine 0. Sine 0 give you 0. Cosine 0 give you 1. So you can see that initial displacement equal to our coefficient A. If you know the initial displacement, then it becomes the number A, the coefficient A. Use similar property to find out B. You can use the second equation, right, to find out B. Use the velocity to find out B. Substitute t equal to 0 back to the velocity equation. U dot 0 equal to minus omega A sine 0 plus omega B cosine 0. Similar things, right? Sine 0 give you 0, the first term 0. And then the second term, cosine 0 equal to 1. And then, so only omega B remains on the right-hand side. So initial velocity, u dot 0 equal to omega B. By using the two initial conditions, or maybe I can say in the other way, the coefficient AB depends on our initial conditions. I think I should say in this way. For this general solution, A cosine plus B sine, the coefficient AB depends only on the initial conditions, U0, U dot 0. Put them back to our general solution. That becomes the solution of our differential equations. For a system, for a single degree of freedom system without damping means C equal to 0. For a single degree of freedom system without damping under free vibration, the displacement response is equal to this equation, described by these equations. At different time instant, you can find out the corresponding displacement values. You just put t equal to your target time. 1 second, 2 seconds, 3 seconds. You may also plot the displacement function using some plotting software like Excel or the other MATLAB or etc. to see how they oscillate with respect to time. But there is one term I did not mention, omega n. Omega n is one very important property. We call that natural frequency. Omega n is one very important property. Please remember this term, natural frequency. Natural frequency. How to calculate natural frequency? This term depends on only two parameters: the system stiffness K and the total mass of the system Mk, K over n, and then take the square root. We call it natural frequency of vibrations. What is the physical meaning? You can see that this natural frequency is within the sine cosine function. They talk about the oscillation frequency. The oscillation frequency. Number of revolution per second. The unit they measure using radian per second. This equation is very important. Natural frequency depends on K, depends on M. You know how to evaluate this based on the member property. Mass depends on, you can calculate mass easily. If you know the density, if you know the volume of the objects, then you can calculate mass. So if you know these two properties, you can evaluate this frequency. They govern this vibration frequency, sine cosine functions. Let you know more clear. You can plot this function on a graph. The graph will look in this way. Plot this equation using Excel or the other thing else. You can substitute some value for U0, U dot 0. Right? When you plot the graph in Excel, you need to fill some number. You cannot plot them symbolically. But for our discussion, we can put them symbolically. So it is the displacement response of a free vibration problems for a single degree of freedom system without damping. Damping equal to 0. This graph tells you many things. It tells you how the system oscillates. At the beginning, here, time equal to 0. At the beginning, time equal to 0. You know the displacement, you know the velocity, because they are the initial condition. Initial displacement, here. Initial velocity, the slope. The slope, mathematically, it is equal to du dt. That means u dot. At time equal to 0, the slope is equal to the initial velocity. If I ask you to plot the graph, I believe that you need to know how to draw it. Okay. The first point, the first point here, at time equal to 0. Actually, the number is equal to the initial displacement and initial velocity. Okay. And then they will oscillate following the cosine sine pattern in this manner. And you observe one interesting thing is that the vibration amplitude remain unchanged. The vibration amplitude remain a constant, remain unchanged. Why we have this property? Based on our previous discussion, when the system oscillates, the vibration amplitude should reduce as time goes on and finally at rest. But in these particular sections, we consider a very ideal scenario. We assume that there is no damping. C equal to 0. If there is no damping, that means there is no any loss, no any energy loss. So for these idealized problems, there is no energy loss. KE can convert to PE, can convert back to KE perfectly without any loss. That's why the vibration amplitude remains unchanged. Not very realistic because for every system you should have some energy loss. But in theory, we can discuss in this manner. So it's something you can observe from this picture. Right? Firstly, the first point tells you the initial conditions, and then the vibration amplitude remain unchanged if you play with undamped conditions. The amplitude, I use U0 here to denote amplitude. And then you can measure the vibration period. Period means the time required to complete one vibration cycle. We call that period. Period is also one important property to describe the dynamic system. Initial point, period, and vibration amplitude. There are some relationship between period and frequency. At the beginning, you have learned what is natural frequency. Natural frequency omega n equal to square root k of n. Remember this equation, omega n. Why I keep emphasizing this term? Because at this moment, I believe that all of you can remember this equation. But near the end of this module, you need to learn many different equations, many different theories. At the end of this semester, I believe that some of you will forget these equations. So in the problem, in some simple questions, I give you directly the k and n, but some students cannot find out the frequency during the examinations. That's why please remember this important formula. If you know singulars, if you know mass, then actually you can calculate natural frequency. Okay, not unknown. I'll go back to this line. There are some relationship between frequency, period, this kind of property. Period, vibration period, Tn, as shown on the previous slide, previous picture, is equal to 2 pi over omega n. So if you know frequency, you can calculate